This subtopic is going to reveal the terms basis and dimension of a vector space. And basis is important to represent the whole vectors in the vector space, and therefore basis build the structure of the vector space. So now we look at the definitions of a basis for a vector space. For that, we need a vector space which is denoted by V, and we need a subset of V, let's say a set S, which contains some vectors from V. And S is called a basis for V if it satisfies two conditions. One of the conditions is S must be linearly independent. And this means if we write K1 V1 plus K2 V2 up to Kn Vn, then the only solution for the scalars K1 up to Kn is, the only solution is 0, and there are no other solution. And the second condition is S must span V. S must span V, and S spans V means that the vector space V is equal to span S. And to show that S is equal to span S, we have to show two things. The first thing is we have to show that V is a subset of span S. And this means for every vector V in V, the vector V must be in span S, and this is also means they are all equivalent by using if and only if symbols. For every V in V, V is a linear combination of vectors in S. V is a linear combination of element in S, vectors in S, V1, V2 up to Vn. These vectors. That means for every V in V, there exists A1, A2 up to An, such that the vector V is equal to A1 V1 plus A2 V2 plus up to, we do the addition, up to An Vn. Okay, and the second condition is span S is a subset of V, and this is obvious or quite straightforward because S is a vector space and S is a subset of V. Why? This is because span S subset of V means that for every W in span S, the vector W is also in V. And this is straightforward because W in the vector W in span S means that W is in the form of a linear combinations of vectors in S. V1 plus A2 V2 plus up to En Vn for some scalars A1, A2 up to En. And we know that V, the vector V1 is in the vector space V, and since A1 is a scalar, therefore the scalar multiplication of A1 and V1 stays in V from the second axiom of the vector space. The same to the other scalar multiplication. Okay, and therefore the whole summation stays in V from the first axioms. It goes under addition operation. So this is how we define space for a vector space V. Let us start with a very important example. Now we consider vector space V as R3 with the standard addition and scalar multiplication, and the set S is a set which contains three vectors, vectors I, J, and K, given as in the slide, and we have to, and S is a basis for R3 because in the previous example, example 3.15, we have seen that we have proven that the set S is linearly independent. Now we have to show that in the second step we have to show that R3 is equal to span I, J, and K. And to do that, we have to show that span I, J, and K is a subset of R3, which is obvious. And you have to know why the first statement is obvious. And the second statement is R3 is a subset of span I, J, and K. Okay. So for the second condition, we have to show that for every arbitrary vectors V in R3, V is a linear combination of I, J, and K. This is obvious because V, for any vector V in R3, V is a linear combination of I, J, and K by using scalars V1, V2, and V3, where V1, V2, and V3 are components in the components of the vector V. And therefore, V is in span I, J, and K, and therefore the vector space R3 is equal to span I, J, and K. And we have proven that the set S containing I, J, and K form is a basis for the Euclidean free space. In this example, we consider the same vector space, which is the Euclidean free space, but the set S that we consider is different, where S consists of the vector V1, V2, and V3 as follows. To show that S is a basis for the vector space R3, firstly we have to show that S is linearly independent. The vectors V1, V2, V3 are all linearly independent. To do that, we write this equation where C1, C2, C3 are vectors on the left hand side, and on the right hand side we have the zero vector of R3. So this is the zero vector of R3, which is equal to 0, 0, 0, because we consider the Euclidean space. Since the scalars C1, C2, and C3 are guarantee its existence, but we need to show that the only the only possible values of C1, C2, and C3 are all zeros, and there is no other solutions for C1, C2, and C3. To do that, we substitute V1, V2, V3 with these values, and we substitute the vector 0 vector on the right hand side with 0, 0, 0, and we simplify this equation. We end up to this new equation. And to find the solutions for or the possible values for C1, C2, and C3, we compare component by component from the left hand side with the right hand side. So this is the first component on the left hand side, which is equal to 0. You get it from the right hand side. And the second component also equal to 0. And the third component is also 0. Therefore, we end up to a systems of linear equation. So this is a systems of linear equation. And this systems of linear equation is homogeneous. Therefore, the system is consistent. But we need to verify that the trivial solution is the only possible solution for this systems of linear equation. To do that, we compute the coefficient matrix. This is the coefficient matrix for the systems of linear equation, and we found that the determinant of the coefficient matrix is not equal to 0. That means the coefficient matrix A is invertible, and therefore the systems of linear equation has only trivial solution. It has only unique solution, which is the trivial solution. Therefore, the only possible values for C1, C2, and C3 are all zeros. Therefore, the set V1, V2, V3 is linearly independent. In the second step, we need to show that R3 subset to span V1, V2, and V3, where the other subset is obvious. The other subset is obvious as explained in the first slide. So to show that R3 subset to the span V1, V2, and V3, we assume that B is a vector in R3, where B is given by B1, B2, and B3 as the components. And we have to check if B is in the space of span V1, V2, and V3. That means we have to show that the vector B is a linear combination of V1, V2, and V3. Means we have to show the existence of scalars C1, C2, and C3. So let us write B is equal to C1, V1 plus C2, V2 plus C3, V3. So then we substitute vectors V1, V2, V3 as given by the question, and the vector B on the left hand side with B1, B2, and B3. And we simplify this equation, and we compare left hand right to the right hand side component by component, and we end up to a systems of linear equation. Remember that we need to solve the system of linear equation to show that the scalars C1, C2, and C3 are exist. Okay, the matrix A here, is the coefficient matrix for the systems of linear equations. And we found that the determinant of A is not equal to 0. That means A is invertible, and that also implies that the systems of linear equation that we found in the previous slide has a unique solution. That means the systems of linear equation is consistent, and the scalars C1, C2, and C3 exist, and therefore B is in span V1, V2, and V3, and therefore R3 is equal to span V1, V2, and V3, and then V1, V2, and V3, and therefore V1, V2, and V3 form a basis for R3. So from the previous two examples, we have seen two different bases for vector space R3, and therefore basis for a vector space is not unique. And we need to identify the standard basis for a well-known vector space. The standard basis for Euclidean n space Rn, which is the general form of R3, the basis contains of n vectors. Let us denote by E1, E2 up to En, where E1 is a vector where the first component is 1 and the rest of the components are all 0. For E2, the second component is 1 and the rest of the components are 0. The same goes to the other vectors. For En, therefore, the last component, the n component, is 1 and the rest are all zeros. So this set S is the standard basis for Euclidean n space. And for R2, whenever n is equal to 2, E1 is I and E2 is J, where the vector I is 2 tuple where the first component is 1, the second component is 0, and J is another tuple with the first component 0 and the second component is 1. For R3, we have I, J, and K form a basis for R3, the standard basis for R3 as given by the very first example that we have considered earlier. This example presents different vector space where the vector space V here is a set of all matrices of size 2 times 2, and the set S, so this is V, the set S that we are considering here is for a set of 4 matrices M1, M2, M3, and M4 as given in the slide. And we have to show that the set S is a basis for all matrices of size 2 times 2. First of all, we need to check that the matrices M1, M2, M3, and M4 are linearly independent. And to do that, we start by writing up this equation. And remember that the right hand side term is the zeroth vector for the matrices, which is a matrix of size 2 times 2, where the all entries of the matrix are all zeros. So now we substitute the matrix M1, M2, M3, and M4 and the zero vector as follows. We simplify this equation and then we compare the left hand side with the right hand side, and we found that the first entry C1 is equal to 0, the first entry C1 is equal to 0, and so on, where we found that all scalars C1, C2, C3, and C4 are all 0, and there is no other solution. There is no other values for these scalars, and therefore the set M1, M2, M3, and M4 is linearly independent. In the second step, we need to show that this vector space is subset to span M1, M2, M3, and M4, and therefore we start by letting an arbitrary vector in the vector space, which is denoted by matrix A. And we write A as a linear combinations of M1, M2, M3, and M4. And we have to show the existence of the scalars C1, C2, C3, and C4. So we substitute the matrices A, M1, M2, M3, and M4. We simplify them and we compare the left hand side with the right hand side of the equation of the matrices, and we found that the scalar C1 is equal to A, the scalar C2 is equal to B, the scalar C3 equal to C, and the scalar C4 is equal to D, and this guarantees the existence of all scalars C1, C2, C3, and C4, and therefore A is in span M1, M2, M3, and M4, and therefore the vector space is equal to the span of M1, M2, M3, and M4, and that's complete the proof to show that this set is a basis for the vector space M2 times 2. The given matrices M1, M2, M3, and M4 form a standard basis for the vector space M2 times 2. In this lemma, we are going to see how a basis is able to represent the whole vectors in the vector space, and therefore a basis structure the vector space. Okay, and the statement of the lemma says that if S, which containing vectors v1, v2 up to vn, is a basis for a vector space V, then every vector V in the vector space V is uniquely expressible as a linear combinations of elements in the basis. Okay, to verify this example, to verify this lemma, we are going to consider vector space R3, and the basis of R3 that we are going to consider here is from example 3.29, where the basis is containing V1, V2, and V3 as follows. And if we pick an example of vectors in R3, let's say the vector X has components 1, 2, and 3, and you may check that the vectors X is expressible uniquely as a linear combinations of V1, V2, and V3, where the scalar C1 is 43, the scalar C2 is -6, and the scalar C3 is -10. So this example verify this lemma. We are going to see another two theorems, where the first theorem, theorem 3.9, says that if we have a basis S with vectors V1, V2, and Vn, and we have another set S prime, which is a subset of V, and for the first statement, if S prime has more than n vectors, means the vectors in S prime has more than n vectors, then S prime is linearly dependent. For example, let's say if we consider R3, we know that the basis of R3, the standard basis of R3 is I, J, and K, where the numbers of element in this basis is 3. So if we have another set S prime which containing V1, V2, V3 and V4, where the elements of S is 4 but the elements of S is 3 and 4 is greater than 3, therefore S prime is linearly dependent. Okay, whenever the number of element in S prime is more than the number of element in the basis. However, if S prime has fewer than n vectors, then it does not span V. From these two statements, we may see that basis for a vector space has similar number of vectors. So even though basis is not unique, but the number of elements in every basis must be equal. The dimension of a finite dimensional vector space V is denoted by dim V. N is defined to be the number of vectors in a basis for V. We have seen earlier that every basis for V has similar number of elements. First example, let us consider the zero vector space where the set only contains one vector, which is the zero vector, and the empty set is the basis for this vector space. You have to try to convince yourself by try to prove it, and therefore the dimension of the zero vector space is 0. The finite dimension vector space, including R to the power of n for Euclidean n space, the dimension of Rn is n. The dimension of all polynomial of degree at most n, the dimension is n plus 1, Rn is n, and the dimension of matrices of size m times n is m times n. And we also have infinite dimension of vector spaces as given by these three examples. The first example is the collections of all real valued functions from negative infinity to infinity. And the second example is all continuous real valued function. And the third example is a collection of all function where m derivative of the function is also continuous. For matrices of size m times n, the standard basis for this vector space is all matrices of size m times n such that one of the entry is 0 and the other entries are all 0. And therefore, the dimension of this vector space is m times n. Let us consider systems of linear equation with 5 variables, and we are required to determine the basis and dimension of solution space of the systems of linear equation. So first of all, we are required to solve the systems of linear equation and determine the solution space. So by using Gauss-Jordan elimination, we first need the augmented matrix of the systems of linear equation, which is given as follows. And then we reduce it to row echelon form. We have this augmented matrix. To find the solution space for the systems of linear equation, we are going to use Gauss-Jordan elimination, and therefore we need to determine the augmented matrix as follows, and then apply elementary row operations following the Gauss-Jordan elimination to get this reduced row echelon form. From this form, we can see that x1 x3 and x4 are variables has leading 1, but x2 and x5 do not has the leading 1. And from here we get the corresponding systems of linear equation from the previous augmented matrix, and the leading variables are x1, x3, x4 because it contains the corresponding column contain leading 1, and the free variables where the corresponding column that do not contain leading 1, therefore x2 and x5 are equal to the parameters t and s respectively, and therefore the solution space is given as follows. Therefore, here is the general solution of the systems of linear equation. We can see that x2 and x5 are free variables, and therefore x2 is equal to s and x5 is equal to t for any real numbers s and t. And x1, x3 and x4 is always 0, but x1 and x3 are depending on the values of s and t. We may write the solution as a vector, column vectors as follows, and we separate the term s and t, and we write it down as follows, where we can see that every solution of the systems of linear equation can be written or expressible as a linear combinations of these two vectors. Therefore, we may show that the previous two vectors, let us denote as v1 and v2, is linearly independent and spans the solution set of the systems of linear equation. So the basis of the solution space is set with v1 and v2 as follows. And the dimension of the solution space is 2 because the basis here has two vectors.